Morning, guys. Today we're going to start our unit on sampling distributions, which is kind of our introduction into inferential statistics. So not just looking at what's going on with one sample, but what's going on with lots of samples to draw a more complete conclusion about our population. We got to kind of get a little vocab out of the way first and some notation. So first thing I want to do is talk about what's the difference between a parameter and a statistic. We've used both of those words before. We've used kind of some of these signal or symbols at different times. I just want to go a little more detail with that. So when we say a parameter is a number that is summarizing the population. So if I wanted to talk about the entire population, I would use move to talk about the mean. We've discussed that before. Or I would use just P for the proportion, or sigma for the standard deviation, nu, that's a capital N, to describe the size of the population. And correlation coefficient, I would use this guy down here, and that's a rho. So looks so similar to a P. This is more like an upside down 6 than a P. That's the Greek lowercase r. So we have rho right there. So a number that summarizes a population is a parameter. Now, if we want to talk about what's going on just in a sample, then we're going to use these other symbols. It's still the same characteristic, but it's not a characteristic of the population. It's now a characteristic of the sample. So for mean, we would use x bar, as we've been doing for a while. For proportion, we use p hat. Remember that hat from all of our regression work means expected. So that's the predicted proportion for the population based on what happens in the sample. So P is what we're going to use in for the population proportion. P hat is what we use for the sample proportion. Standard deviation is just going to be S, or it can be SX, standard deviation of X, whatever it happens to be. Usually we throw a subscript on here. For sample size, we're going to use a lowercase n, and then correlation coefficient, we've done this before, that's just that lowercase r. So the way I keep these straight, whether I'm talking population or a statistic, parameter or statistic, if I'm dealing with a population starts with P, so does parameter. So I need a parameter to describe what's going on in population, but if I want to talk about a sample, I'm going to use a statistic. That's very important when we get into writing hypothesis statements and things like that, where we're writing about what's going on in the population, but we're using sample data to kind of come up with those conclusions. So we need to figure out, are we writing it in terms of statistic, or are we writing it in terms of parameters? So if I'm dealing with population, I use my parameters. If I'm dealing with the sample, describing what's going on in the sample, I use my statistic. Now that we've kind of got that out of the way, let's talk about the 3 different types of distributions that there are that come from a sample, and then how we distinguish between them and carry into these sampling distributions. Okay, so the first 2 that we're going to discuss, we've used these many times, but I want to talk about them and how they kind of compare or relate to what's going on with the new one, which is a sampling distribution. So types of distributions, we have population distributions, sample distributions, and then in a second we'll describe a sampling distribution. So population distribution, as we know, shows every individual in the population, and always has the same distribution. Sorry, I should say same distribution. So one population can only produce one distribution. So let's look at another one of my collections I've got here, and that's my poker chip collection. So as you can see, I've got a lot of red, blue, white poker chips here. And if I want to describe the breakdown of red, white, and blue, that's just a distribution. So on that distribution, we know that we have 415 total in the bucket, 418 total poker chips. So notice I'm using that capital N because it's the population size. And then my RWB, that's just representing what's going on within a single category. So I've got my categorical variable, color of the chip. So I have 120 red ones, 184 white ones, and then 114 blue ones. So if we were to kind of calculate the proportions and draw out the distribution on that, my proportion of red ones is 0.287, just 120 out of 418. So about 30, a little bit under 30%. My white ones are going to be 0.440. So that's the proportion of white chips in this bucket right here. So about 44, 45%, or it is 44%. And then on the proportion of blue ones, 114 out of 418 is 0.273%. So a little bit underneath the red one here. So this is the population distribution, and these are some of the parameters that we've calculated. We have the sample size, population size. We have population proportions for each one of those colors. No matter how I grab those 418, it's always going to produce this one picture right here. Now, contrast that with what's going on with a sample. So let's say that I have just a sample of 20 of them. So we just have 20 chips from my population. So that 20 might look like this right here. So I just grab 20 random chips, red ones, white ones, blue ones, just grabbing a handful until I've got 20 of them right there. And then what you can see is the breakdown on that. So in this specific sample that we have here, I had 7 red ones, I had 7 white ones, and 6 blue ones in that sample. Well, we can obviously see that it's different in the numbers. So what's going on in a sample distribution? In a sample distribution, we don't see every individual in the population, we see every individual within a single sample. So I don't know about everybody, but I know what's going on in this 20. So I know what the breakdown of red, white, and blue for those 20 of them. Next thing we know is samples from the same population can have different distributions. So if I grabbed a different 20, it may not be 7, 7, and 6. It might be 7, 7, and 6, but it's not necessarily going to be the same. So every single distribution could very well be different in that case. Every single sample could have a different distribution. So that's kind of the difference between a sample distribution and population distribution. This one population, all of these is going to have this one distribution, but its samples can look very, very different. So I know I'm not saying anything revolutionary right here. I'm just trying to make sure we can kind of get this idea of building through samples and how samples look similar to, but not necessarily exactly like the population. All right, so if we were to calculate those proportions, so notice that I've changed it from proportion of red to sample proportion of red. That's what that p hat represents. So my sample proportion of red is 0.35. So 35% of my sample were red. Okay. My white ones were also 35%, 0.35. And then my blue ones in the sample proportion was 0.30. So a little bit different between what we see population-wise and what we see sample-wise, but it was pretty close to it. So maybe I feel kind of confident that I had a somewhat representative sample. All right, so that's sample proportion, population proportion and sample proportion. Well, let's see how that ties into sampling. Okay, what is a sampling distribution? A sampling distribution says don't just take one sample and then tell me what it looks like. It says take all possible samples. So if I was to grab those 120, or 418 chips we had, and then grab 20 of them, and then grab the next 20, and then the next 20, keep replacing every time, and just keep grabbing samples of 20 until I've got every single way I could get those 418 rearranged into groups of 20, that's all my possible samples together. That's a sampling distribution. It's a distribution of all possible samples from one population at one size. So I could have a sampling distribution at size 20 samples, at size 30 samples, at size 4 samples, but within one sampling distribution, you can only use one sample size. So all possible samples of the same size from the same population. That's what a sampling distribution is. Now, we don't ever sit down and do every single one. What we do is we look at kind of theoretically what would happen based on the way the population is distributed or characteristics are distributed throughout. But we're going to use this phrasing, so I'll make sure we understand. Sampling distribution is not one sample, it's all possible samples. Once we've got all possible samples, we're going to calculate the same statistics. So I'm going to find the same characteristic in every single sample. So I'm going to figure out what was the average height from every single sample, or what was the standard deviation of number of winds for every single sample. What was the correlation coefficient from every possible sample? So we're going to get the one characteristic, and measure that for every single sample so we can compare that characteristic. So we're just really saying, how does this trait show up through every possible subgroup in our population? That's what we're doing with a sampling distribution. And then we're going to show the distribution of that statistic. So I've gone through and I've done a few samples of size 20. So the first one was that sample that we just looked at a second ago. And if we want to look at the proportion of white chips in a sample of size 20. So the proportion of white chips in a sample of size 20, the first sample we had 7. So 35% of them were white chips. Then I went through and I got another sample that had 11. And so that sample had 11 white chips in it, so that's 55% white. And then I just went through and did a different sample that was 8 chips, so they were 40% white ones. 11, again, got a different 11 to get 55 white chips. Then I had a couple of chips at 9. All right, so this is what a sampling distribution, the graph of sampling distribution is going to look like. It's always going to be a dot plot or histogram, some type of quantitative data, because it's a measured statistic. So when we're dealing with samples, we can have categorical data or quantitative data. So sometimes we'll have a histogram, sometimes we'll have a bar graph like what we were just looking at. But a sampling distribution is always quantitative, because all it is a distribution of measurements that we made, not counts. Remember, categorical data, you're going to have counts, and you're going to say, what was the count? But not whether we're dealing with categorical data, color of poker chip, or we're dealing with the proportion of a specific color, now we've taken that categorical, how many in a certain color, to what are all my proportions of that one color, and we've made that into quantitative data. So sampling distributions are always going to be quantitative, which means we're going to use our quantitative summary statistics to kind of get to them. All right, so this is what a sampling distribution looks like. It's what it means. Let's kind of talk about some other characteristics of it. First thing is the topic, this idea of sampling variability. What is sampling variability? Well, variability is just how different things are. So that just means we expect differences from one sample to the next. Well, we saw that. I had one sample of 20, and there were only 7. Another one had sample that had 11 white chips. And then I had some that had no variability. They ended up having the same number of white chips. So we're expecting there to be some difference from one sample to a different sample. It's kind of a common sense thing there. Why we need that idea is because of this idea, variability of a statistic. So variability of statistic is just the measure of those differences. So if these are my proportions of white chips, if I measure the differences of all these proportions, then I'm getting the variability in the proportion of white chips in a sample. And the way we phrase that is just standard deviation. That's all standard deviation is, right? Measure of differences, average difference. So standard deviation of the statistic. So well, I told you back last semester that we were going to get into a lot of different ways to talk about standard deviation. We've already introduced quite a few. Vocabulary terminology is really important on it. So when you see standard deviation of the statistic, this is standard deviation of a sampling distribution, not standard deviation of a sample or standard deviation of a population. And they say standard deviation of a population, it's standard deviation of a population. You're using sigma. Standard deviation of a sample, you're going to use S. Standard deviation of a statistic, okay, that's going to be different calculations depending on what the statistic is and how we're doing it. So standard deviation of the statistic means go find standard deviation from your sampling distribution. And we're going to get into that through these next few lessons about how to do these calculations. All right, now, what's the point in all this? Well, I think it should be kind of an intuitive thing why you would want to do that. If one sample should give us a decent estimate, a whole lot of samples should give us the perfect estimate, right? That's what that is. So to get a trustworthy estimate of a parameter, because that's what all this is about. The whole reason we look at samples so we can get an idea of what's going on in the population. So to get a good estimate of what's going on in the population, two things we can do. One, choose an unbiased estimator. What the heck does unbiased estimator mean? Well, an unbiased estimator is just one where the mean of the sampling distribution, or the expected value of the sampling distribution, so in our case, the mean of the the sample proportion of white chips. So the average of all of these proportions together needs to be equal to the parameter of the population. Well, the parameter would be the proportion of all white chips. So that's what a sampling or that's what an unbiased estimator is. Okay, so the average from this should equal whatever's happening out in the population. Well, let's calculate this average real quick. So if we did 0.35, 55, 40, 45, so on. So if I average those 6 proportions together, and technically we would do every single possible sample, so all million, billion, trillion, however many samples of size 20 there are for my 418 chip. If we did all of those samples together and got their proportion of white chip, that would give us this value right here. But we're going to estimate it right now just because I don't want to do all million, trillion, billion of those samples. So let's just use this as kind of a snapshot, and that's going to come out to be 0.458. So 0.458. That's the expected proportion of white chips based on those few samples I've done. Well, if we want to compare that to what's actually happened in our population, the proportion of white chips in the population, well, if we look back, the proportion of white chips in our population was 0.44. That's kind of interesting right here, that 0.44, that 0.44 is really, really close to what we have just in a few samples. So more samples means we would have got even closer to that 0.44. So that's what we're talking about with an unbiased estimator. And these are the unbiased estimators that we work with. So we're usually going to, when we measure the same statistic, calculate the same statistic, it's going to be one of these guys. We're either going to calculate the mean for a bunch of samples, or we're going to calculate the proportion for a bunch of samples, or the standard deviation, or we could do variance if we need, or the correlation coefficient for those samples. So these are the statistics that we would measure, and then we know that whatever we get from summarizing them should tell us what's going on in the population. It's just going back to that drawing conclusions that we've been dealing with throughout the whole course. So that's one thing that we can do to get a good estimate of the parameter. Pick something that gives a pretty good estimate. But not everything we measure could. So we'll talk later about some things that you might not want to pick, but these are what we're going to focus on. The second thing we can do is use a large sample size. And we've talked before about large sample sizes, minimizing variability and things like that. But if you have a large sample size, you're going to reduce variability because individuals have smaller weight. So if I get one really wide, way out there value, he's not going to have as much influence because you've got a lot more people towards the center to balance him out. So each individual has a smaller weight, and more information from population makes the sample more look like the population. I mean, that seems like a common sense thing, right? So the larger our sample size is, the better that snapshot gets of the population. So obviously we're going to get a better estimate of what's going on in the population. All right, so that's it for sampling and distributions. Big thing we need, big takeaways we need, is taking all possible samples of the same size, calculating the same statistic, and then getting an average of those, or standard deviation from those, to get our standard deviation of our statistic. All right, that's it, and I will see you guys in class tomorrow.